Notice you only had 5 questions in the homework. I'll work more problems in class than you have as a homework assignment for this section. My third question, still looking at arc length, you have y is equal to the natural log of cosine x. And our formula for arc length, just to remind you, is s is going to equal the integral from a to b, where the region ends, where the region begins to where the region ends, of the square root of 1 plus the derivative squared with respect to x. And whether that derivative is written as dy dx or f prime of x, irrelevant. Now, looking into this, I can say, well, okay, I know in this problem I'm giving you the natural log of the cosine of x. So, since it's y, I'll go ahead and say dy dx, the derivative of y with respect to x. Derivative of the natural log of the cosine x. Derivative of any natural log is 1 over what's inside the function times the derivative of what's inside the function. When I say derivative of cosine, be negative sine. And so I know this is just going to be negative sine over cosine. That's going to give me negative tangent of x. And I'm positive of that. So I'll say, okay, I have the derivative. My formula requests the derivative squared. So clearly, dy dx squared is just going to be tangent squared x. The negative is irrelevant. So now, I can say, I know inside of this square root, I'm going to end up with a 1 plus tangent squared. And we already know 1 plus tangent squared x. Hopefully you remember, it's one of your Pythagorean formulas from trigonometry. 1 plus tangent squared is secant squared. So when I go into this square root formula, I'll say, well, the arc length of this region, it starts at 0, it ends at pi over 4. It's the square root of 1 plus tangent squared x, which now we'll go ahead and say, well, that's nothing more than secant squared. So it's the integral 0 to pi over 4. Square root of secant squared is just going to give us secant. And then I can say, we can integrate this. This is your, you have a formula in the back of your book for it, but you might also just have it memorized that the integral of the secant function is the natural log of secant plus tangent. So I can say, okay, whether you use, and that is a formula I would provide. You do not have to have the integral of the secant memorized. But I would say, okay, so arc length is going to equal the integral of secant, which is natural log of secant plus tangent inside of the absolute value. And then this is going to be evaluated from 0 to pi over 4. So now I can say, well, okay, evaluating this shouldn't be that bad. And I would say exact answers only. That would make the problem more cool. So I would say, okay, s is equal to the natural log of the secant of pi over 4 plus the tangent of pi over 4. Then obviously minus the natural log of the secant of 0 plus the tangent of 0. And all you'd have to do just real quickly is think of a unit circle. At pi over 4, that splits the first quadrant. And at that value, both your sine and cosine are the square root of 2 over 2. And at 0, your cosine is 1 and your sine, your cosine is 1, your sine is 0. So I can say, okay, the secant is nothing more than the reciprocal of the cosine of pi over 4, which would be 2 over the root of 2. 2 divided by the root of 2 is nothing more than the root of 2. So I can say, this gives me the root of 2 the tangent of pi over 4 is going to be 1. So I'll have the natural log of the root of 2 plus 1 minus the natural log of the secant of 0. So the secant of 0 is the reciprocal of the cosine of 0. Cosine of 0 is 1. Secant of 0 is 1. Hey, man. Thanks for texting me to let me know. Tangent of 0, well, 0. So I'll get the natural log of 1 plus 0. So I can say, I know this second term is just the natural log of 1. Natural log of 1 is 0. Thus, the final answer in exact form is the natural log of the square root of 2 plus 1. Okay? So, this next one, to make this arc length even better, is I want to combine it with a proof. I want to use the arc length formula to prove that circumference of a circle is 2 pi. We know circumference is nothing more than the arc length all the way around this circle. So the way I'm going to work with this is say, and I should say that this is circumference of a unit circle. Not all circles have circumference of 2 pi. So I know in my unit circle, if I'm looking at that, this is where the r value is 1. The equation for a circle radius 1 is x squared plus y squared equals 1 squared. So I know that the equation for this circle is x squared plus y squared is 1. Now, you'll notice some of the problems in this section require the techniques I'm doing right here in this one. Because my formula is 1 plus dy dx quantity squared underneath the square root with respect to x. Do you remember how you're going to have to take the derivative of an equation like this? Yes! Implicit differentiation. Beautiful. I think it's section 3.7 in your book. So you just say, okay, take the derivative with respect to x implicitly. So you know that the derivative of x squared is just 2x. Technically you'd say dx after it, but doesn't contribute anything. So I'll just say, well, it's just 2x times the derivative of x with respect to x, which is 1, plus 2y times the derivative of y with respect to x, which does contribute something, so you need it. Yeah, if you like the y prime notation, that's adequate. I frown upon it, but it's adequate. Why don't you like it? It's sloppy. Yeah, because y prime, what is y prime? Y prime could be dy dz. You don't know. You don't know, you don't know. I mean, you're like, well, yes, I know because there's x's in it. But, I see. But I would not count on. This just looks better.
I just like it for these problems. I feel like it's easier to look at.
It's quicker. Then the derivative of 1, of course, is 0. So now, I'll go in through here and say, well, my goal is to solve for dy dx. I'll do that. dy dx. We know it's going to be negative 2x divided by 2y, which would reduce down to negative x over y. But then you say, but we're squaring it. Yes, we are. That's going to equal x squared over y squared. Now, I need to keep on working with it. You might say, how will I know whether to keep on working with it or to stop? Notice, The other problems, whenever I squared the dy dx, it was a function only. So the first three problems we worked in this section, my derivative, the first one, the derivative was just a constant. That's the easiest scenario. The second and third one, the derivative was a function of x. You just plug it in, integrate it, should work pretty nicely. I can't integrate a function in x and y and take the integral with respect to x. So I know that something needs to be worked with this. So I'll just say, well, I know the part inside of that square root is going to be 1 plus dy dx quantity squared. That's going to give me 1 plus x squared over y squared. I'm just trying to tamper with this to remove the y squared. So the first thing I'll do to tamper with that, and keep in mind it's probably quicker to work with this before you start the integration problem than once you start it and have to write the integral of all this and simplify it at that point. It's easier to go ahead and simplify it first. So I'll say, if I want to simplify this, I could combine these fractions by getting a common denominator. This is y squared over y squared. So I can say, I know that this is going to give me y squared plus x squared over a common denominator of y squared. Do you see what we're going to do? Do you see? Do you see? Do you recall how we simplified implicit differentiation problems back in Calc 1? To get to the final simplified answer, typically you had to use the original equation in your derivative. So the original equation is x squared plus y squared is 1. X squared plus y squared is 1. And so now you might be thinking, well, okay, great, John, you got rid of the x. I thought you wanted to get rid of the y. Oh, I do. But getting rid of the x was a bonus. Well, not a bonus in the bonus sense. You're like, extra points? No. Now, the y squared down here, I need to represent it somehow. So what I'll do, again, I know y squared should equal 1 minus x squared, right? So I'll say I know that this is equal to 1 over 1 minus x squared. That gets my what's inside the integral in terms of x. So this 1 plus dy dx, which is going to be the interior of my square root function, simplified to this. My goal was to get something nice in terms of x. I think I've achieved that goal. So I start the integral. I'll say, okay, arc length is equal to, let's think about this. Okay. So can I integrate from, let's say, -1 to 1, and it represent the arc length of my object? No. And you're like, well, why? Because it's not a function. So what I would have to do, I need to separate it up. I could integrate from -1 to 1, and it's going to give me the arc length at the top, and then I just know to double it. I want to do even better than that. I'm going to integrate from 0 to 1 and say, well, that's going to be the arc length of the first quadrant. Because of symmetry, every other quadrant's the same thing, so just multiply by 4. So I'm going to say the arc length is 4 times the integral 0 to 1. That's going to find the arc length in this first quadrant from x is 0 to x is 1. So I'll say the arc length from 0 to 1 of this function, which is simplified down to 1 over 1 minus x squared.
What about the plus 1 you put on the dy dx side? What was that?
The plus 1...
You add 1 both sides up there. And I get you over here, but on this side...
Oh, right! Now, are you saying what happened to
no,
that?
on the other side, equal sign. You put a plus 1 there too. But
No, okay. So this, I was thinking ahead there, Adam. I was saying the inside of my square root has to be 1 plus the derivative squared. So that's where that 1 came from. So I said, okay, 1. So I was thinking, what's going to go inside this 1 plus the derivative squared became 1 plus, this is my derivative squared. And then I got a common denominator to get that as a y squared over y squared. Okay?
I thought you were just adding both sides.
No. I was saying, this is what's inside the square root, so I need to work with that before the problem to simplify it down. Now you might be thinking, well, that's not very simple. Oh, but it is. Because we know that a square root of a fraction is the square root of the components of the fraction. So the square root of 1 is 1. So this is going to equal 4 times the integral, 0 to 1, of 1 over the square root of 1 minus x squared. Does that ring a bell? Inverse sine of x. The derivative of inverse sine of x is 1 over the square root of 1 minus x squared. Thus, the integral of this function and so now I can say, well, okay, this is 4 times the inverse sine of 1 minus the inverse sine of 0. Group around that. Now I can just say, well, the inverse sine of 1, that's asking you, when is your sine function 1 such that the inverse sine is defined? Inverse sine is only defined for sine values between negative pi over 2 and pi over 2. So I can say, well, I know that the sine of pi over 2 is 1, thus the inverse sine of 1 is pi over 2. The inverse sine of 0 is 0 because the sine of 0 is 0. So I can say this is just giving me 4 times pi over 2 minus 0. 4 times pi over 2, 2 pi. Done.
Isn't that kind of cheating since only we know that the unit circle is, that the rest units are pi?
No, but see, that's the whole point is we had to get 2 pi, so, since it was a verification or a proof, you could either put quod erat demonstratum at the end, or a little check mark would be sufficient. So, yeah, you knew you had to get to 2 pi.
I'm just saying that the whole reason we know that like the inverse sine of that is based on the fact that we're dividing up 2 pi, like the inverse sine of 1, for example, is pi over 2. The only way we know that is...
Oh, you're saying it's cyclical reasoning. I agree with that. Yeah, I would agree. But it's still an application of the integral, so I liked it because of that sense. But I agree with you. It's cyclical reasoning.
It's a proof. It's got to be.
Well, you have to have some axioms that it's always dependent upon. It's just that we're kind of going backwards and trying to prove an axiom. Like, okay. Now, next thing I want to do in this section. And I'm not 100% sure there's homework problems assigned to this. I can pick some more if you want. No. Oh, okay. Surface area of revolution. We've done volume of revolution, but not surface area of revolution. So 8.1 part 2. So 2 main topics in 8.1. The first topic is arc length. Pretty simple. The second topic is surface area. And I would argue it's not that bad either. Whenever you think of any curvilinear surface, say like that, we just worked problems that were working with the arc length. So if I said, can I find the arc length from some point A to some point B? Well, of course we can. We have already saw how to do that. So I could find the arc length from some point A to some point B, given that this curve is an integrable curve, which I would say it would be. Now, what the surface area is going to do, let's say if I want to take this area or this region developed by this curve in the x-axis and I want to rotate it about the x-axis. And I want to find the surface area of the solid of revolution. So I'd say, well, okay, surface area, all I'm going to have to do is find the distance of the outer region times the surface area of the circle formed by the solid. So I'll just say, well, okay, I know that my radius here, the r value, is going to be whatever the function is. I'll say the r value is f of x. That's going to be the distance above the x-axis. So my surface area formula, I'll say surface area, in general is equal to 2 pi r times whatever the arc length is. But now, what I've shown here is that the r value of any region rotated about the x-axis is simply the function's value. So this is going to simplify to 2 pi times f of x. And then our arc length formula is that integral, which has the square root of 1 plus f prime of x, quantity squared, or dy dx squared. Now, that has to be times delta x. So I could say if that would be the surface area of one partition. If I wanted to find the surface area from A to B, it's just going to be the integral of all of this. So I could say a generic formula, surface area, is going to be 2 pi times the integral from A to B of f of x on the square root of 1 plus f prime of x quantity squared with respect to x. So, a problem based upon this. Let's start off with an easy one, then get to a fun one.
So why do you have to incorporate arc length?
Oh, I thought you were going to say, why do you have to start with an easy one?
No.
I need to.
Just quickly, I'm just sort of, I guess, logic-wise, I'm stuck here, but
Okay.
why do you have to multiply by arc length? Why would it not just be the integral of 2 pi r?
Okay, so think about that. If I tell you I want you to find the surface area of a cylinder, what are you going to do? You're going to say, well, I need to find the area all the way around it. How would you do that? Well, you could pull it apart. You could pull that cylinder apart, and you'd see that whenever you pulled it apart, it's nothing more than a rectangle where the width of that rectangle is the circumference. You'd say the circumference of this going all the way around is going to be 2 pi r. That's going to form the base here. And then you'd say, okay, what's the other dimension? Well, the other dimension would be the height. What would be the height of this? I could say, well, that's whatever, 2 pi rh would be our volume of the cylinder, where h is this. We're just saying now, we don't know what the height is, so we're having to call that f of x. You okay? So 2 pi r f of x. And then the r is going to be the function here, and then the f of x, the r is the function from that, and then our arc length, which determines, and I mislabeled this here, the h is going to be the arc length of the function, if you think about it, rotated about the x-axis.
Yeah, okay.
Yeah, don't overcomplicate it. It's not bad. It is not bad. So now, if I look at a problem like this, this will be number 5 out of this section, I think. Yeah. I'll say y, if I just give you a linear function and say it's 4x plus 3, I want to find the surface area between 0 and 1. So I know that my formula still involves f of x and the derivative squared. So f prime of x is simply 4. So f prime of x squared, 16. So my surface area I'll say my formula is 2 pi times the integral from 0 to 1. And then inside your integral, you have to put the function f of x. So the function f of x is 4x plus 3. that's going to be multiplied by the square root of 1 plus the derivative squared, 1 plus 16, 17. And I know that this is integrated with respect to x. So what I would do in this case is, that root of 17 looks kind of ugly in there. I'd go ahead and factor it out and say this is simply 2 on the root of 17 times pi on the integral from 0 to 1 of 4x plus 3. Which then we know that's just going to be 2 on the root of 17 pi times the group 4x squared over 2. 2x squared plus 3x evaluated from 0 to 1. When we evaluate this polynomial at 0, we know we get 0. So when we evaluate it at 1, we'll get 2 plus 3, 5. So that'll be 5 times this group. Final answer, and I would want an exact answer. 10 on the root of 17. And I'm leaving the pi over there. It's probably better form to say 10 pi on the root of 17. That looks better.
You read my mind. I was going to ask about that.
Yeah, it was bugging me. Now, if that were, I'm getting used to writing imaginary numbers in other classes, and if that were an imaginary number, the I should go last. That's what I would say. But pi, no. I, yes, pi, no. So that was what I call an easy problem from that section. Go ahead.
That's the surface area, not counting the, like when you cut it off at A and B.
Right, exactly. It's the surface of the region, not those points on it.
Okay.
Yes, yes. That's a very good question there. So it's just the surface area of the region in between. Ooh, which I'll say, hey, yeah, I already accounted that for that. That's why I did dashed lines there. No, it's really not why, but yes, absolutely. Looking at number 7. Oh, sorry, number 6. So, what if I give you a simple looking function like the sine, but I already said that this was my hard example. Like, okay, how hard could it be? Not that bad. So, sine from 0 to pi. I say, well, okay, I know the formula is going to ask for the derivative squared, so dy dx cosine. So we know the derivative squared obviously is cosine squared. And so just going ahead and setting this up, I can say, I know that my surface area is going to be 2 pi times the integral. So I'm just plugging in exactly what I see here. 2 pi times the integral, where it starts to where it ends, 0 to pi. These problems are very formula-based. You just use the formula, plug it in, it works nicely. F of x, sine of x. The square root of, 1 plus cosine squared. Oh, I started to say that's an identity, but actually, no, it's not. So 1 plus cosine squared dx. Do you see what you would do at this point in the problem?
No,
Sorry,
do you?
I amused myself. You would use a U-Substitution. That's what you would do. So you'd say, hey, I think I want to let u equal cosine x, and then du is going to be the negative sine of x dx. That's going to get rid of that term. This isn't going to be a one-step solution, though. This is the first step in our process to a solution. So I'll say, okay, I will allow u to equal cosine of x, du negative sine of x dx. So this is going to give me the surface area is the negative of 2 pi on the integral 0 to pi And then I'll get the square root of 1 plus u squared du.
You need to change it.
Yeah, you need to change your limit.
Oh, yes, I do. Thank you. Yeah. I'll change them. I was thinking to leave them blank and then account for that later, which might be a good idea, but I'll go ahead and change them. Thank you. So I can say, I know u evaluated at 0 is the cosine of 0, which is 1. U evaluated at pi is going to be the cosine of pi, which is negative 1. So I'm going from 1 to negative 1. Ooh, this is what I'll do. I don't like going from 1 to negative 1. I'll go from negative 1 to 1 and keep my sign positive out front. Thank you. Does this make sense now? So I said, I really should be evaluating from 1 to negative 1. I'll say, well, just keep it from low to high, negative 1 to 1. That changed the sign out front. So now, even at this point, though, sadly, this is not something that we can integrate very easily without using another technique. So we use substitution in the first step.
Trig substitution.
Now trig substitution. 1 plus u squared, you can say, well, okay, now I'm going to allow u to be x times the, sorry, not u is x. U is going to be a tangent theta, so just tangent theta, since a is 1. So I'll say, now I'll allow u to be tangent theta, and then the du, derivative of tangent is secant squared theta with respect to theta. Now, I also know that 1 plus u squared, that's going to be 1 plus tangent squared, which is secant squared. But I'm going to have the secant squared inside of a square root. So I know that that square root is secant, so that's just going to be secant. So I'll say, okay, this is going to equal 2 pi. And I'm just going to leave my limits off for right now. I'll worry about them in a second. And I'll say, okay, the square root of 1 plus u squared becomes the square root of secant squared, secant theta. So now I can say, all right, du is secant squared d theta. So when I multiply by du, secant squared d theta, this becomes secant cubed d theta. And what I'm going to do is leave my limits off. Could you go ahead and say, well, your limits are just in terms of u, so you could say negative 1 is equal to tangent of theta. Theta would equal the inverse tangent of negative 1. That would be fine if you wanted to go ahead and change your limits right now. That would be fine. I'm going to opt not to and just leave them blank. It would be wrong to put negative 1 to 1, but it's okay to leave them vague or blank for right now. So I'll say I'm going to go ahead and integrate in terms of theta, then I'll introduce a trig triangle to evaluate back in terms of u in the next step. So the integral of secant cubed theta, that's, I think, number 48 in your book. Let's see. Haha. Oh, 42 actually works easier. It's more direct. 42 gives you secant cubed u. Excuse me. The 48 is the secant of n power, so it works for anything, but specifically 42. And what I typically do anytime I'm using a formula in the back of the book is I'll just put a 42 over the equal sign. And then, so I know that the integral of the secant cubed is going to be 1/2 secant u tangent u plus 1/2 the natural log of secant plus tangent plus c. If you're like me, I know it hurts you to use these formulas because you feel like aren't I supposed to be learning how to integrate these? That's one of the fun yet frustrating things about Calc 2 is you get to tons of integrals you just can't integrate. As much as you want to learn every technique of integration, it's impossible. So we can just say, well, okay, I'll accept the fact that I'll look up the integral of the secant cube, and actually you might memorize it. That one would be easy to memorize, wouldn't it? 1/2 secant tangent plus 1/2 natural log of secant plus tangent. He's looking at me like, are you crazy?
There's not a way that you could doing like the trig identity and then do the power reduction and.
Well, okay, I don't want to say there's not a way, but I'll just use the formula because the second you say you can't do that, somebody, yes you can. So I don't want to say no, but I don't see it directly. So it calls me to stutter. So now which doesn't take much. I'll go to my next page and say this is going to equal 2 pi times the group 1/2. The formula says secant theta tangent theta. Plus 1/2 the natural log of secant theta plus tangent theta. And then the C won't be necessary because we're going to be using an evaluation on this in just a moment. So I can say, okay, I would like to get this back in terms of U by using a trig triangle. My trig triangle is going to be defined by the fact that U is equal to the tangent of theta. So I know that the tangent of theta is U over 1. So I'll say, okay, here's my angle theta. Opposite is U, adjacent is 1. So this hypotenuse is the square root of U squared plus 1 squared, or 1 plus U squared, either way. And I see that that was what was in my problem in terms of U, so I'm thinking, okay, that's a good thing. Whenever this 2 pi multiplies through this, obviously the 2 and the 1/2 eliminate, so that'll make it easy. I'll be left with pi times the group. And if you wanted to put the limits of integration in this step, because somebody, and oftentimes teachers would say, a definite integral cannot become an indefinite integral. So if you wanted to show your work beautifully without changing your limits of integration, you could just say, well, I know that this is still U equals -1 to U equals 1. That would be perfectly fine. That's just telling the reader you chose not to convert the limits to theta, but it also reminds you don't put those theta terms -1 to 1 in. And up here I would say this is U equals -1 to U equals 1. So I'm getting it back in terms of U now. So I would say, okay, secant of theta. I know secant's the reciprocal of cosine. Cosine would be 1 over the hypotenuse. This is just hypotenuse over 1. Secant of theta is going to be the square root of 1 plus U squared. And that's being multiplied by the tangent of theta, which automatically we already knew was U. So I'll say plus the natural log of the absolute value, secant square root of 1 plus U squared, plus tangent, which we knew was U. And this is, again, from -1 to 1. I don't have to put U equals because now the only variable in there is a U. So my final answer here, I'll get pi times the group. When I evaluate this at 1, I'll have the square root of 2 times 1, square root of 2, plus the natural log of the square root of 2 and then plus 1. I'll say that's my first group. When I evaluate at -1, when I plug a -1 in here, I'll have in the first group, I'll say minus 1 plus negative 1 squared, that's 1 plus 1. Square root of 2 again, times negative 1. Square root of 2 times negative 1, negative square root of 2. Plus the natural log of the absolute value, square root of 2 minus 1. I'll close the group there. So trying to simplify this beautiful mess, I'll have pi times the group. Collect like terms. You have a couple of square root terms in there. The square root of 2 minus a negative square root of 2, that's 2 on the root of 2. So I'll have pi times the group, 2 on the root of 2. What could we do with our logarithms? Brian's always good about doing this. He does all the time. So what would you do here, Brian?
You're talking about what I did on the last.
Yes, I loved it. So you just say, you could combine these logarithms by saying it's the natural log of
The 2 plus the square root of 2 plus the 1 divided by the square root of 2
Like
minus
it.
the 1.
plus the natural log of square root of 2 plus 1 over the square root of 2 minus 1. I dropped the absolute value because I knew that this term was going to be positive anyway. Square root of 2 plus 1 and square root of 2 minus 1 being positive terms. That would be my best exact final answer. Are you kind of thinking this is fun? Well, I see some nodding.
I can tell you want to use the board. It would be totally okay with us if you did.
I'm actually not. I feel more organized this way.
You sure they weren't messing with you?
Hmm?
You sure they weren't messing with you about that?
Oh, no. I'm on a committee for new room assignments and stuff. That's strong in discussion. Looking at section 8.3, please do notice.
Oh, it would have a plus C, right?
No.
No.
It's a definite integral.
Ah,
No plus
Gotcha.
C. So 8.3, please note there is no section 8.2 in your homework assignment nor in our list of sections to be covered. Centers of mass. So let's say, for example, I give you a finite set of masses acting as forces on a coordinate plane. So I'll say, let's say I have a 5 kilogram mass. Oh, I need to put 5 kilograms. Well, now that just looks like a big dot. So ignore that and just say that's 5 kilograms. And this is the coordinate 3, 4. Okay, let's say I have another one over here, a little 1 kilogram mass, not 0.1, at negative 8, 2. I'll have a 7 kilogram mass down here at the ordered pair 1, negative 1. And finally, another mass at negative 3, negative 6. And this is going to be a 3 kilogram mass. Now, I wanted to start off basic like this. Some of you have already been through class where are like, oh, okay, I understand torque and moments and centers of mass. I already got that, John. Others of you have not, so I have to start off on a level playing ground, assuming you know nothing. So, if I wanted to go in here and say, well, okay, let's find the average x value in this. Well, that average x value, what it is it's nothing more than what's called the moment about the y-axis. In other words, if you think of all these forces acting on the plane, think of them acting vertically downward, how would it balance? Or is there a torque in the y-axis? And I could say, well, okay, yeah, I think there's going to be a torque. It's not going to be perfectly balanced. It's going to be tilting to one side or the other. And the amount of that torque or that force is what we're looking for. And then I could say, so the average x value is going to be a moment about the y-axis divided by the sum of all masses. So I'll just say, now, if I were just trying to find the x value, the average x value, so x bar, I'd simply just say, well, okay, take the x coordinate. For example, this one is a 3 times its mass, 3 times 5. Plus, I'll go in the counterclockwise direction. I'll say my next one is going to be plus a negative 8 times 1. Then plus a negative 3 times 3. Plus a 7 times 1. Or sorry, 1 times 7. I'll keep the same order. So I know the ones to the right of the y-axis are forcing the x values, the average x value to the right, the ones on the left forcing it to the left. Now, all of this is divided by the sum of the masses, which is just 5 plus 1 plus 3 plus 7. Now, if you multiplied and added all those x values together, 15 plus negative 8 plus negative 9 plus 7, it's going to give us a 5. So I can say the net total force, it's actually going to be torquing this xy axis towards the positive x-axis, since I have a positive 5 for the average x value. So the force is going in that positive direction, not the negative direction. So if I were thinking of this as a board, the board's going to be leaning this way. But now, it's a lot harder to lean a board with a force the heavier the board is. That's where the sum of those masses comes into play. So I could say, so is there any relevance to that 5 plus 1 plus 3 plus... You bet there is. So I could say, well, those sum to be 16. Now, all of these forces that will either torque this xy plane in the horizontally in the right x-axis direction or the left x-axis, they're forces about the y-axis. So we call them moments about y-axis. Okay, so similarly, I need to do the same thing for y. I'd say, well, let's find the average y value. I already know I'll be dividing by the sum of all the masses, so that's going to be 16 again. But the average y value, I would just say, well, I know that I have a y value of 4 times a weight of 5. Or I should say times a mass of 5. I have a y value of 2 times a mass of 1. Both of those forces would torque my xy axis upward. So right now, if I had the plane and just those, it'd be wanting to torque in that direction. But that's going to be countered by these weights. They're wanting to force it in the other direction. So I could say, well, those weights are going to be accounted by a y value of negative 6 and a mass of 3. So I'll say plus negative 6 times 3. And plus negative 1 times 7. So I'll get y bar is equal to, if I add up all those y values there, 20 plus 2 minus 18 minus 7, I'll get a negative 3. I get negative 3 over 16. So what we would call the center of mass, or the centroid of this finite example, and a finite example just meaning a limited number of points in the plane. So the centroid, another word for center of mass, is just that ordered pair x bar, y bar, which would equal 5/16, negative 3/16. Okay, now, if we're talking about any region, I can could say, let's say I have some curve now with an infinite number of points in it. This just looks like the cosine function from 0 to pi over 2. Doesn't have to be any specific function though. So I'd say, well, okay, what if I had some generic function and I want to find the x bar, y bar of this region? So clearly if I just eyeballed it and said, well, I bet it's about right there. Well, the way I would get that is I'd say the average x value is always finding a distance from the y-axis. So I'd say, by definition, x is the distance from the y-axis, the weight each x value has. So how do we dictate the weight of an x value? Unlike before where I could explicitly say in our finite points, hey, this x value of 3 has a weight of 5. This x value of 1 has a weight of 7. Now if you choose a particular x value, what dictates its weight? The height of the curve at that x value. The smaller the height of the curve, the less relevant that x value is into the weight of the object. So I'd say, okay. Oops. Oh, that's ugly. So I'll say the height at this x value, and remember, this is an infinitely thin strip, and it's perfectly drawn rectangly. You don't see any imperfections there. So, So I can say, I know this infinitely thin strip at this distance of x, it has a width of delta x and a height of f of x. So here's my first formula. X bar is equal to what we call the moment about the y-axis divided by the sum of the masses. And again, the reason that this confuses some people, they're like, why in the world is the average x value the moment about the y-axis? Because those x values are torquing the force about the y-axis, similarly to how the y values torque the force of the x-axis. So they're going to be a moment about the x-axis. So I could say, okay, in this case, this moment about the y-axis is going to equal, summation notation. I could say it's the sum of I equals 1 to n, where you have infinitely many thin strips in there, of the x value, the distance from the y-axis, whether it's positive or negative, I'll just say x times the function's height at that point, that gives you the weight of that x value, f of x, times the thickness of that, delta x. Okay, and all of this is going to be divided by the summation of all of the masses. That's just going to be the sum from I equals 1 to n of whatever under the curve f of x, delta x. So I could say this is just going to equal, the numerator is nothing more than the integral from where the region begins to where the region ends. That's where you're going to put all these little rectangular regions in between. I'll say A and B. I'll go ahead and label this. Yes, A looks a lot like 0 and B looks like pi over 2 if this is the cosine function. But I just want to be a generic case that works for all of them. I'll say the integral from A to B of x times f of x dx. Divided by the denominator of the integral of the sum of the masses, which is just going to be the integral from A to B of f of x dx. This is what's important here, guys. That's the average x value in a centroid formula. Now, am I going to ask you to come up with this drawing and show me where? No. Hopefully you see where I'm getting it from, but if you don't, it's not the crucial thing. The crucial thing is being able to use this. Now, as far as the average y value, I'd say, well, the average y value is going to be the moment about the x-axis divided by the summation of the masses. And if I have, I'll draw it under this same curve, if I was trying to figure out the average y value, what I do is I would have, again, some rectangular region in here. And again, its height is going to be f of x. But the y value is going to be the distance from the x-axis. And here's the tricky thing. The most representative y value within this rectangle is going to be half the f of x function. So I could say this y value, which is the distance from the x-axis, I know I would prefer to integrate with respect to x because the thickness of this rectangle is going to be with respect to x. But that y value there, I don't want to put a y. So I'll just call it, well, it's 1/2 f of x. That will be the distance there. 1/2 f of x. And then this is delta x. Gorgeousness. And so you say, okay, if I want to find the moment about the x-axis, then what I'm going to do is I'm going to take a summation of all rectangles that look like this. So I could say, okay, that's going to be a summation from 1 to n, 1/2 f of x, that's the y value, 1/2 the function's height, times the height of the function, that's the weight of that y value, times the thickness of the curve at that point, delta x. All divided by the summation of our masses, summation of f of x delta x. And that's, well, I think I'll just leave the 1 to n off the summation. I should have for all of them because it's implied to be 1 to n if you don't put anything. Okay, so now I'm afraid I've run out of room here, so I'll come down here. The average y value, hopefully you can see, this is just going to be 1/2 times the integral a to b of f of x quantity squared. Divided by the integral from a to b.
Can you dx?
Oh, I do. dx of f of x dx. Does it make sense where those came from, guys? Now, does it make you feel better knowing that you will be provided these formulas, or are you like, those are easy to memorize, don't need them?
Both.
Both. Okay, so a problem in this section. Oh, again, I want to start off with an easy one, then get to a fun one.
So why aren't you teaching any physics?
Did this make sense, really?
Yeah, I wish I had have asked you for help like last semester when I did that engineering class. I really, really do.
I actually am teaching a physics class in the fall, but it's not here. It's at the co-op I'm teaching at. I'm teaching a high school physics class there. It's going to be awesome.
Well, because in ENS we just...
Can we pretend to be high schoolers and go?
Can I transfer that?
You could. Let's say, I need to give you the function first. What if my function is f of x equals 6 minus 2x? Does the red show up as well? Yeah. Yeah. So if f of x equals 6 minus 2x, my goal is to find the centroid of this region. And you'd say, well, that's a pretty simplistic region. That's why I'm starting with this one. We know it's going to have a y-intercept up here at 0, 6. And I made it look like the x-intercept's the same. So drawing not to scale, this would be 3, 0. So just thinking realistically, you'd say, well, okay, I know the average x value is more towards this direction. The average x value, it has to be less than 1/2. Is that obvious, guys? Because the x values close to 0 and 1 are weighted much more than the x values close to 3. The height of the curve gives the weight of the x value. So I'd say, well, the average x value, probably at 1. Well, the average y value. The average y values are weighted more down here. Because I'd say the distance from the x-axis, again, so I'm thinking it's probably like 1, 2 or something like that. Okay. And also, since it's a triangle, I bet it is. But hey, I want to use calculus to solve that out. So I'd say, okay, the average x value. Formula says it's the moment about the y-axis divided by the sum of the masses, which we have our formula up here. It's just going to be the integral from where this region starts to where this region ends in terms of x. So 0 to 3 of x times f of x. Well, x times f of x, I should have already done that before I set this up, but we know when we multiply x by f of x, we're going to get 6x minus 2x squared inside there. And then we're going to integrate this with respect to x. My denominator is going to be the integral from 0 to 3 of f of x, which is just the 6 minus 2x. And I've already put my dx in the numerator, so that's fine. So I need to simplify this out, and I can say, well, okay, in the numerator here, oh, no, I need a dx down there too, don't I? That's terrible, John. So I can say, in this numerator, we're going to get 6x squared over 2, that's 3x squared, minus 2/3 x cubed, evaluated from 0 to 3. We'll divide that by the integral from 0 to 3 of 6 minus 2x. That's going to give us 6x minus 2x squared over 2, so minus x squared. Again, evaluated from 0 to 3. This average x value, the first part of our center of mass, our numerator, we're going to have 3 times 3 squared, that's 9, minus, oh no it is not, 3 squared is 9, but times 3 is 27. 3 squared is 9, yes, but that's not what it is. So I get a 27 there, minus 2, oh I knew the answer was 9, yes, that's what, no, I didn't. Minus 2/3 times 27 is going to be minus 18. So the numerator is going to be 9. My denominator, I'll get 6 times 3 is 18, minus 3 squared is 9, so 18 minus 9 is 9. The average x value, 9 over 9, 1. Okay. So I already know that x value of the center of mass is 1. And I also already know the summation of the masses is 9. So there's no need to find that again. When I find the average y value, all I need to know is that, well, the average y value is the moment about the x-axis divided by the summation of the masses. The summation of the masses is 9. The moment about the x-axis is our 1/2 the integral from a to b, 0 to 3, of f of x quantity squared. So we need to square this group 6 minus 2x. So I'll say, okay, 6 minus 2x squared with respect to x. I already know my denominator is 9. So I could even rewrite this as, well, this is going to give me 1/18 the integral from 0 to 3, 6 minus 2x squared squared. If you need to write it out beside each other and FOIL it, please do that. But I'll say, well, I know it's going to be a 6 times 6 for 36. Then it would be 6 times negative 2x is minus 12x. Then you'd have another minus 12x. for a total of minus 24x. Then you would have negative 2x times negative 2x for plus 4x squared. That's all of that squared out. Now we're integrating with respect to x. This should work nicely. So I'll say the average y value is 1/18 times the group, 36x minus 24x squared over 2 minus 12x squared plus 4/3 x cubed and then we're evaluating this from 0 to 3. So when I plug in a 3, obviously when I plug in a 0 I get a 0. When I plug in the 3 I'll have 36 times 3, 108. Minus 12 times 9, hey, that's 108. And then 4/3 times 3 cubed, that's going to give me 4 times 9 is 36. Well, yeah, I was just thinking of that as 3 squared because this 3 is going to cancel out one of them. So 3 squared is 9, 9 times 4 is 36. 36 divided by 18, 2. So my average y value is 2, my average x value is 1, so the center of mass of this object is about right there. So I do want the ordered pair format answer, 1, 2, that's what we do. Now, hopefully you're thinking, but God, that's too easy. Okay, a harder example. Now, sadly, the homework assignment in this section, you're going to think I'm getting too easy on you. 4 problems? God. So, actually, I was complaining at the beginning, going, I can't do the homework. Maybe even I can. I can do 4 problems and post it on mine. So, yeah, I think I can handle that. I probably will post them. But I do want to look at one more problem out of this section. So it's fair if you do 4 problems homework. I do 2 example problems in class, I think. That should be sufficient. This is my harder example problem out of 8.3. And then hopefully we'll have time to get to one of my favorite topics of the semester. Usually students hate it. Taylor polynomials. It's something that will haunt you through the rest of your calculus, math, forever and ever. Throughout you'll never be able to get away from it. Boy, that is an important. I need to rethink my motivation talk there.
They should thin out the class.
So, 8.3, number 2. So, let's say I give you a natural log function, and I want to find the center of mass of the natural log function from x equals 1 to 3. That's actually pretty easy to think of because we know the natural log function, it goes off to negative infinity, but the natural log of 1 is 0, and then it grows pretty slowly. So I'd say the region that we're looking at is right here, where this is 1, this is 3. So this is the point 3 ln 3, and this is our point 1, 0. So trying to find the average x and y component of that region. So I'm thinking the average x value, I am certain, common sense tells me that the average x value is closer to 3 than it is 1 because the weight of the x values is more towards 3 than it is 1. So I'd say if I just had to make a random guess at the x value, I'd say 2.4. Now is that right? Of course not, but I guarantee it's closer to 3 than it is 1. So we need to use some logic to kind of make sure our answers are correct in that sense. And our average y value, well, I'm not sure what the natural log of 3 is. Let's see, oh, that's just asking what power of e is 3, so it's a little bit greater than 1, because e is 2.718281828. So this is asking what power is of 2.7182828 is 3, so it's going to be like 1.05 or something. So I can say, if this is 0 and that's like barely 1.0 something, then my average y value is a lot closer to 0 than it is the 1.0 whatever something. Did someone actually find it?
1.098.
Ah, thank you, 1.098. So I know it's closer to 0 than it is 1.098 because there's more y values in this region than there are up there. So I would say if I had to guess on the average y value, I'd guess 0.3. But we need to do better than guess. So we'll say, I would suggest breaking this problem into its components and just say, let's find the sum of the masses first. Excuse me. That's just going to be the integral from 1 to 3 of the natural log of x with respect to x. Now, if you need to use integration by parts on that, you can. Hopefully this is one of those that's already occurred so frequently that you have it memorized. It's x ln x minus x. But I will put above the equal sign integration by parts. Let u equal natural log of x, dv equals dx. And I promise you, it will work out to be x ln x minus x. We'll evaluate that from 1 to 3. And then I'll say, okay, so the sum of the masses, that's going to be 3 ln 3 minus 3. And then it would be all of that minus 1 ln 1 minus 1. Well, I know that the natural log of 1 is 0, so really all I have here is negative 3 minus a negative 1 is going to be negative 3 plus 1. The summation of the masses is going to be 3 ln 3, negative 3 plus 1 minus 2. So that's going to be an important component of our answer. I probably shouldn't have circled it, though. I probably should have underlined it. Now, I need to find the moment about the x-axis. The moment about the x-axis, this is our, I'll say, we know it's 1/2 the integral from 1 to 3 of f of x squared. Well, okay, that's going to be the natural log of x squared. Again, unfortunately, this is not one of those, and I need to put my dx. It's not one of those that you can simplify that easily. You must use integration by parts on this one, and I don't have it memorized right off the top of my head like I have this one. We don't use natural log of x quantity squared as much. I'm going to say, let's let u equal the natural log of x quantity squared. Then dv is everything else, which is just dx. There's nothing else in there. So be careful when you take the derivative of u. You must use the chain rule. So you'd say, okay, a group to a power, the derivative of a group to a power. Bring the power down in front, times the group to the one less power. Chain rule says times the derivative of what's inside. Derivative of natural log of x, 1 over x with respect to x. Have to have all of that there. Now, obviously, v is just going to be x whenever you integrate 1 dx. So, I'll try here. I'll say the moment about the x-axis is going to equal 1/2, and I'll have times the group, u times v, x, ln x, quantity squared. There's no way to simplify that quantity squared on that natural. Please don't think you can write that as 2 natural log of x. That's only if only the x is squared. There is no simplification for the group natural log of x squared. So I'll say x ln x squared, u times v, minus the integral And I'm going to go ahead and bring this 2 out. So I'll say minus 2 times the integral. And notice what's inside of that interval now. d du, that x cancels that 1 over x. So you're left with just the natural log of x in there. That's nice with respect to x. So we already know that integral. It's x ln x minus x. So I'll say the moment about the x-axis, and I need to put in around my bracket, this is still being evaluated from 1 to 3, and then I don't need to put the limits on that interval. I can say the whole thing's going to be evaluated from 1 to 3, and there's only x's in there, so obviously it's in terms of x. So I'll say the moment about the x-axis is 1/2 x, natural log of x, quantity squared. This 1/2 and the 2 would eliminate. I'll have minus the group x ln x minus, that's the integral of the natural log of x. So I'll say minus the group x ln x, and then minus x. I've kind of used a bracket where I should have used a parenthesis, but that's okay. I can still say this entire group is evaluated from 1 to 3. Just to simplify signs, I'll show one more step. 1/2 x ln x quantity squared minus x ln x plus x. Evaluated from 1 to 3. When we evaluate this at 3, we can see we'd get 3 over 2 natural log of 3 squared minus 3 ln 3. I'm not seeing any terms that will combine right now, plus 3. And I'll say we need to subtract from that when we evaluate this at 1. And I thought I wouldn't have room, so I brought it down to the next line. But there's actually not much to worry about when you evaluate it at 1, because we know the natural log of 1 is 0. This entire first term is 0. The entire second term is 0. All I would have is a 1 for the x. So I would have had plenty of room up here. I didn't think I would. But I'll say minus 1. So the moment about the x-axis here is just going to be 3 over 2 ln 3 quantity squared minus 3 ln 3 plus 3 minus 1 plus 2. So right now, I have enough information to find the average y value. Remember, I guessed that the average y value was 0.3, and I promise you, honestly, I do not know what it is exactly. But we can find it exactly. We can say, we know that the average y value is the moment about the x-axis. So I would want it in exact form, and then we'll also find the decimal approximation just to kind of check our thinking. The only thing I'm certain of is that it better be closer to 0 than it is 1.09. So I need to enter this into the calculators. So I'll say 3 over 2. Natural log of 3
Got square.
Thank you. And actually, I'm going to turn off that new mode. It's bugging me. And you have to make sure to close the natural log and close the group that the natural log is in, and then square it. So you have to make sure that that's right. Yeah, that's right. Minus 3 ln 3 close plus 2 close divided by the group 3 ln 3 minus 2.
How do you go back, just since you've mentioned that, how do you go back to the other mode? If you're going
You just go mode and then arrow up. So the reason for demonstration purposes, because it scrolls off the screen and you can't see the beginning part, I just arrowed over to classic. So I'm getting 0.397 approximately there. Which is closer to 0 than it is 1.098. So I'm satisfied with that as, yeah, I think that should be right. Now the average x value. We know that we find it by finding the moment about the y-axis. And I can say, well, the moment about the y-axis we had in our formula, that was just the integral from where the region starts to where the region ends, 1 to 3, of x f of x. Well, that's going to be x ln x in this case. So I say, well, it has to be the integral of x natural log of x. Again, how are we going to evaluate that integral? I parts again. So you say, okay, u is always the logarithmic term. So this time, dv has to be x dx. du is our 1 over x dx. Whereas v, whenever I integrate this, it's going to give me 1/2 x squared. So I can say, okay, I think this should work. The moment about the y-axis is going to equal u times v. So 1/2 x squared natural log of x minus the integral of v du. So I'll go ahead and say minus 1/2, factor that 1/2 out in front. The integral of v du, x squared times 1 over x gives me x with respect to x. I'm integrating this from 1 to 3. So I can say, okay, this should work really nicely. When I plug the, actually it'll work really nicely if I finish it. So I do need to integrate my remaining term in there, but it'll be easy. So the moment about the y-axis, 1/2 x squared ln x minus 1/2 times 1/2 x squared, that'll be minus 1/4 x squared. So when we evaluate this at 3, we'll get 9 over 2 natural log of 3 minus 1/4 times 9, so minus 9 over 4. When you evaluate it at 1, you can ignore the first term since the natural log of 1 is 0. So then you'll just get minus the group negative 1/4. Which is, of course, going to be plus 1/4. Negative 9 over 4 plus 1 over 4 gives me negative 8 over 4. This is just going to give me 9 over 2 ln 3 minus 8 over 4 minus 2. So I have my moment about the y-axis. My average x value is the moment about the y-axis divided by the sum of the masses. In this case, we know that that's 9 over 2 natural log of 3 minus 2 divided by the sum of the masses, which we had up here earlier. Had to scroll down. 3 natural log of 3 minus 2. And so then we can say this should give us the group So I was expecting this answer to be closer to 3 than it is 1. I predicted 2.4. I don't know. Let's see. 9 over 2, natural log of 3. Close the natural log, minus 2, close the numerator. Divided by open 3, ln 3, close, minus 2, close the denominator. 2 point, well, not as close to 3 as I thought it would be, but it's certainly closer to 3 than it is 1. 2.272 rounded. Now, keep in mind, I don't just want the approximate answer. I'll ask for exact and approximate, so both of those are part of our solution. Is this okay? Yeah, go ahead, John.
The 2 came from adding the 1.
It did. It was minus 2 because you had negative 9/4 plus 1/4 is negative 8/4 minus 2. Yeah. It's just you have to subtract the lower limit, and inside the lower limit, the only thing that amounts to anything is the 1 times negative 1/4.
Would you want us to put that in an ordered pair?
Say that again.
Would you want us to put that in an ordered pair?
Oh, yeah, please. Yeah.
I mean, even though it's really funky.
So your ordered pair solution, 2.272, comma, 0.397 would be good.
You wouldn't want us to put the exact form in there.
Nah, that would look too ugly in an ordered pair. Now, Taylor polynomials, guys. Say that again. Oh, yeah, I am.
Yeah, it's a beautiful day. Come on. We want to go play
That
tennis.
is true.
I have a bunch of stuff to do. Not to be at church at 5:30.
Well,
Beautiful day.
so I won't even work a problem with this then. We'll just talk about what a Taylor polynomial does. So, what have you done before in classes whenever you've asked to predict a curve? Like in section 4.1 of this book, there was a section called linear approximation. And you've done things in earlier classes like this too, where you say, oh, okay, if I give you, and you don't have to write this down, this is just the formation of the logic of this next section. What does a Taylor polynomial do? Why is it important? It's probably, I'd say, the 4th most important thing we're going to do. Substitution, number 1. Integration by parts, number 2. Partial fractions, number 3. Taylor polynomial is probably number 4. And what a Taylor polynomial is going to do is, let's say I have some curve here, and I should put it in the xy coordinate plane, and we have a point on that curve. Let's say that this is at the x value of a. Okay, so we know at this x value of a, what if I said, I want you to determine a linear function that estimates that curve at that point? We did this all the time in Calc 1, where you said, okay, what do I need to do for equation of the line going through that point? I need to know a point and I need to know a slope. So you said, oh, okay, this point is the point AF of A. Okay, what's the slope of the curve at that point? Well, the slope is just whatever the derivative is evaluated at A. And then, whenever you think of, well, a linear equation, this goes back to pre-calc. You said, in order to have a line, point slope formula says y minus y1 is equal to m times x minus x1, right guys?
Yeah.
Where x1, y1, that's simply a coordinate in the plane. So, what I'll do is, let's say, why not let your x1, y1 be AF of A? That's what I would say. So, if this is x1 and this is y1, because y1 is a particular y value. x1 is a particular x value. So this becomes y is equal to, or sorry, y minus y1 becomes y minus f of a equals the slope, which is f prime of a, times x minus a. So the equation of our line going through this point on this curve is y equals f of a plus the group f prime of a times x minus a. So we did this early on in Calc 1. We didn't talk about it as, ooh, it really is a good estimate of the curve right around A. We didn't talk about that early on. Then in chapter 4.1, they brought up linear approximations, where it said the linearization of a function f of x, let's call it L of x. That was all it asked you to do. It said the linearization of a function at a point x is f of a, where x equals the point A, plus the derivative of that point times x minus a. Okay, now that's all well and good. But now we're saying, why stop at a linear approximation? That's such a simplistic approximation for a curve that could be way more complex than a linear function. So that linear function would be an excellent approximation. Ooh, I can't even draw a straight line here. That linear function would be an excellent approximation for a region, you know, around A, fairly close. But then you say, well, what if I want to approximate the curve more exactly? Ooh, wouldn't a quadratic function do a better job? The quadratic function can start accounting for some curves. Then if you think, well, if a quadratic function is good, how about a cubic? How about a quartic? How about a quintic? How about, you know, a 20,000th degree function? The higher I get, the better it's going to be. Taylor polynomials enables us to find the exact degree function, or sorry, the exact coefficients of any term function that we want in this case. I could say, whatever this arbitrary function is, I could call it, you know, a sinusoidal function or something like that. I could say, find a 10th degree polynomial using Taylor polynomials that approximates this sine function at x equals pi over 4 or something like that. The better, the higher power you get, the longer it's going to be a good approximation for the function. That's where we're going to start off next class. Now hopefully you haven't, well, I'm going to skip it then. But it's really, really good stuff. I like it. Okay, guys.